Welcome to Non-Euclidean Geometry Lesson 13. In this lesson, I'm going to talk about horocycles. Horocycle in Greek means boundary circle, and we'll see that this topic is related to circles. A horocycle is a continuous curve defined by a set of asymptotic boundary parallel lines with one point of the horocycle coming from each line. The points of the horocycle are defined in a particular manner, which we'll get to. It'll take a few slides to actually define it. So we're going to start simple and then we'll build up to the definition. So let's start here. Consider two asymptotic parallels, P delta and Q delta, as shown in the figure. As indicated by the notation, P is on one line and Q is on the other. And both lines have direction delta. If P and Q are such that the trilateral P delta Q is equiangular, in other words, these two inner angles are equal, then we say P and Q are corresponding points. In the figure below, P and Q are corresponding points on asymptotic parallels P delta, Q delta. So just to maybe give you a little preview here, these 2 points are actually on a horocycle. And if we had more asymptotic boundary parallel lines, then and we picked a point on each one of these, you would actually get a horocycle. But again, we'll get to this later, but I'm just kind of slowly building up the definition here. We have a theorem here. It's an if and only if, so we'll need to prove it in both directions. Given two asymptotic parallel lines, P delta and Q delta, so P delta, Q delta here, points P and Q are corresponding points on these lines if and only if the perpendicular bisector of PQ, in other words, this line here, that's perpendicular to PQ and divides the distance between P and Q equally. So in other words, MP equals MQ, is parallel to P delta and Q delta in the direction delta. So let's prove it in the reverse direction first. Assume the perpendicular bisector of PQ, this line here, is parallel to P delta and Q delta as shown in the figure. By theorem 40, we have the trilaterals MP delta and MQ delta are congruent because we have MP equals MQ, and then we have a right angle here and a right angle here that are equal. And so given congruence, we have that alpha equals beta, and then by definition, P and Q are corresponding points. Let's go in the other direction. Assume P and Q are corresponding points on these two parallel asymptotic lines, P delta and Q delta. By theorem 40, we again have these two trilaterals, the top one and the bottom one are congruent because now we have alpha equals beta, and we also have MP equals MQ. That's our perpendicular bisector. By symmetry, if P delta intersects this M delta, say a point A, then Q delta would also intersect M delta at that same point A, but that's a contradiction because we have that P delta and Q delta are parallel. That was the condition of the theorem. And so it must be that M delta does not intersect P delta or Q delta. In other words, they're parallel, and that's what we wanted to prove. So given that P and Q are corresponding points, the perpendicular bisector is parallel to both P delta and Q delta. In the context of the following theorems, a line M is said to be equidistant from lines L and N if the perpendicular, i.e. shortest distance from any point on P any point P on M to either line L or N is equal. So in other words, if we have a line M here and we're saying L and N are equidistant from M, and you pick any point on M, then the shortest distance from M to L needs to equal this shortest distance from P to S, from this point P here. In other words, PR needs to equal PS. And if we picked another point P prime, then the shortest distance from P prime to L would need to equal the shortest distance from P prime to S. One fine point here that's easy to miss is this shortest distance is not constant. So in other words, RP does not need to equal R prime P prime. So in other words, if L and N were boundary parallels, asymptotic boundary parallels, they would be getting closer and closer. So this shortest distance would be getting less, and going in this opposite direction here, they would be getting further apart, or vice versa, depending on which direction they're converging on. So we have a theorem given two asymptotic boundary parallels, P delta and Q delta, not this figure here, just not to confuse you. There exists a line M delta, each of whose points is equidistant from and parallel to the two given lines. And if you're interested in a proof, it's from this book that I've referenced many times by Gons, and I think I've given you the link to the Internet Archive location where you can borrow the book if you want to have a look at the proof. Given two asymptotic parallels, A delta and B delta, and a point R on A delta, there exists a unique corresponding point on B delta. So we have this line here, which we'll call L, and that's our A delta, as it goes through a point A and goes in the direction delta. And then we have this other line N that goes through point B and goes in direction delta. And we're given a point R on L. And we want to find the corresponding point S, which I've drawn down here, but we have to construct that. By theorem 50, there exists a line M which is equidistant between L and N, let P be the projection of R onto line M. So project R down onto line M. So this is 90 degrees. And then select J on L and K on N such that PJ equals PK. Those two distances are the same. In addition, select the point S on N such that SK equals distance RK. Then we have this side equals this side equals this side, and we have a 90-degree angle here and here. So by side angle side, this triangle here, PSK, is congruent to the triangle PRJ. And then we get the two other angles being equal once we have this congruence. In other words, PRJ equals PSK, PRJ equals PSK, and then these little angles in here, RPJ, RPJ, and SPK are equal. Okay, so we still don't know that S is the corresponding point. So we have more to do in this proof, which I'll get to in the next slide. By theorem 40, A, J, PM, and trilateral B, K, PM are congruent. They have an angle that's the same, and then PJ and PK we know are the same length, so they have an inner side and an angle that are equal. And so knowing that, we have that JPM is equal to KPM. And since RPM, this angle here, which we constructed at the beginning of our proof, is equal to 90 degrees, and RPM equals RPJ plus JPM, and JPM equals KPM, and these smaller angles here are PJ and SPK are equal. We have that SPM must also equal 90 degrees, since these two smaller angles that make up SPM equal these two small angles here, and we know these two RPM is equal to 90. So long story, but what that says is if we know this angle down here, SPM is 90, and also the angle on this side here is 90, that means that R, P, and S are collinear, so this is a straight line, and we also know that P, R, J, this angle here, is equal to PSK. So we have that R, S, delta, in other words, this trilateral that I'm tracing out here, is an equilateral triangle, and thus, by definition, R and S are corresponding points, since this angle here is equal to that angle here, and they're both on this trilateral. Okay, so a bit of a difficult proof, but here we have it. So let's continue. We haven't quite finished the proof of our theorem. We need to show uniqueness. So let's do that. Assume there are 2 points, S and a T, on B delta that correspond to R. And without loss of generality, assume that the angle here, beta, is bigger than alpha. And so we have 2 trilaterals, ARSB, and the interior angles are alpha. And then we have another trilateral, ARTB, and the interior angles there are beta and beta here. So if we draw it as shown here, we run into a problem because from Euclid's elements, we know the exterior angle to this triangle RTS is greater than either of the opposite interior angles. So that implies alpha is greater than beta, but we assumed beta was greater than alpha, so we have a contradiction, and so there can't be a second point that's corresponding to R. Okay, we're almost there. We have a few more theorems before we get to the definition of a horocycle, and I'm going to leave the proofs to a reference in the book by Wolf. I'll give you that reference again, although I've mentioned that book before, and you can borrow it from the Internet Archive if you like. So if points P, Q, and R lie on 3 asymptotic parallels, all pointing in the same direction, so P delta, Q delta, and R delta, such that P and Q are corresponding points, and Q and R are corresponding points, then P, Q, and R are non-collinear. That means they're not on a straight line. Okay, so that's one. And then second theorem is if P, Q, and R lie on 3 asymptotic parallels, P delta, Q delta, and R delta, so they all point in the same direction, such that P and Q are corresponding points, and Q and R are corresponding points, then you have transitivity in the sense that P and R are corresponding points. So we're finally able to define a horocycle here. Consider a line L in a direction delta and a point P on it. So here's our line L. For each asymptotic parallel N, I'm showing just one of them here, N, there exists a unique point Q on N that corresponds to P. The locus consisting of P and all such corresponding points, So in other words, this Q, this point here, here, and all the ones in between are the horocycles. So this curved line here is a horocycle. We know it's curved from the first theorem on the previous slide, where we well, we didn't prove it, where we mentioned that the three corresponding points are non-collinear. So we know these points here are not collinear. The horocycle is determined by line L, point P in a direction delta. The asymptotic parallels to L in the direction delta and L itself are known as radii of the horocycle. So for this horocycle here, this is a radii, this is a radii. And again, well, I can't draw all the lines, but there's an infinite number of lines here. Since the given horocycle is determined by P delta, we denote it by P comma delta. So this is one horocycle. It follows by theorem 53 that all points in the horocycle are mutually corresponding points. So Q is corresponding to P, this point here is corresponding to Q, this point here is corresponding to this point, and all the way through on this. Thus, a horocycle can be determined by any of its points. In the figure from the previous, well, from on this slide, the P delta is the same as Q delta. So, and if I gave a name to this here, if I called this R, then R delta would also represent the same horocycle. If we take another point P prime here on L, then the horocycle P prime delta is different from the horocycle P delta. So this point here gives rise to another horocycle, and I could have picked a point here, and that would be another one. So you basically have an infinite number of these horocycles lined up one after another. Distinct horocycles which have the same direction and hence the same radii are referred to as codirectional horocycles. So this one here, and if I drew another one here, they would all be codirectional horocycles. Horocycles have some interesting properties. While they're not circles, they have some similarities to circles. I'll mention a few of them here. There exists a unique circle with a given center which passes through a given point. So that's true for circles. In comparison, there exists a unique horocycle with a given direction which passes through a given point. We kind of highlighted that on the previous slide when we set the notation there, like P delta, where P was the point and delta was the direction. Two concentric circles share no points. In other words, two circles with the same center, but they have different radii. In comparison, codirectional horocycles share no points. So we saw two of them on the previous slide that, of course, they didn't have any points in common. A unique radius is associated with each point on a circle, and a unique radius is associated with each point on a horocycle. A tangent to a horocycle at a point on the horocycle is defined to be the line through the point which is perpendicular to the radius associated with the point. This is the same as the definition of a tangent of a circle. Horocycles appear differently depending on the model used for the hyperbolic plane, and we saw a few of the models in the previous lesson. So if we use the Poincaré disk model, then each one of these lines, like I'm pointing to here, these are asymptotic boundary parallels. And so if you pick a point on here, the corresponding points actually form something very close to a circle, and you get this really pretty looking diagram. This is what I'm pointing to here, this circular-like figure is a horocycle. And of course, you'd have another one out here, another one out here. So just one being shown in the figure. And this comes from the Wikipedia article on horocycles, and I'll give you a link to that also. Okay, so that's the last slide and the last lesson that I have on hyperbolic geometry. There's a whole lot more to study. The two books that I've been referencing quite a bit from Gons and Wolf would be your next step if you wanted to learn more about the topic of hyperbolic geometry. I think the book by Gons is a little bit more readable, and as I mentioned several times, you can borrow that from the Internet Archive, and I think they let you keep it out until someone else requests it. So that's it. I have another lecture on elliptic geometry that I won't go into as much detail as I did here for hyperbolic geometry. I'll just have a single lecture, but it'll be on the long side, and I'll put that up once I get the video recorded for that.